Thank you. Right, so we start the last topic here on feedback amplifiers, but the approach is a little more of an analytical approach than a circuit design approach. For everything else we've done before, in the course you've seen how to basically design various things from power supplies to oscillators to waveform generators to filters, multivibrators and the like. This time we're going to look at one of the sort of more theoretical, if you like, analyses that is involved in electronic design, and it has to do with the whole concept of feedback, which we met on a number of occasions, but we're going to see what the effect of it is on circuit designs and things that you would have met before, but maybe not quite in the same way. Okay, so we start this evening. And well, we met some of this in various forms already, both here and in the signals and systems class, if you did that with me. Essentially a feedback, well, we spoke about feedback networks, and a feedback amplifier is one where you take some part of the output and you send it back through another little network and combine it with the input. Right, so the amplifier, normally if the amplifier is not operating in the feedback mode, this is normally what we call the open loop operation of the amplifier. So you send a signal into the amplifier and you get the amplifier out and it's in the open loop mode. As we saw from previous discussions on it, when you provide feedback to a system, a couple of things can happen. If you provide negative feedback, we saw that what tends to happen is that the system corrects itself. So if there are changes in the output, the feedback subtracts from the input and tends to stabilize the performance of the system. And on the other side is that if you add if you took some part of the output and the feedback was positive, where it added to the input, then what happens is that the output of the system tended to behave in a different way. It would either go until it's saturated, or it would create some sort of performances for us which may be desirable, for instance, in oscillators. All right. So this particular diagram, of course, is showing a negative feedback, and what we want to see is what would be the effect of putting negative feedback around that amplifier. And that amplifier could be anything from an op-amp to cascaded amplifier design made of individual transistors and so on, right? So again, just in what we just said, just to summarize it in a slide, at the amplifier itself, some part, you have the input to the amplifier, and typically the input to an amplifier for our purposes may be either current or voltage. Might be either current or voltage, and that now goes through the amplifier, which amplifies, of course, the current or voltage. Some part of that is fed back, and again, we can feed back either current or voltage, and we sum it up through a mixing network. Normally, the networks may not be that complex in mixing network. It may sometimes be just a set of passive components in there. So we have current. Essentially, we have I or V going this way, and we can have I or V coming back that way. So it gives us 4 possibilities to play with. All right, and we can see for both the voltage, for instance, sorry, let me just go in the sequence that I have. If the amplifier is amplifying current, we can feed back either voltage or current from the output coming back in. And if it's amplifying voltage, we could still feed back either voltage or current, depending on the particular configuration of the circuit that we're dealing with. All right? So the summing network is a series. In the case of the summing junction itself, or the summing network, right? If you have a series circuit inside of here, what it's going to do is going to feed back a voltage back into the system. And if it is a shunt voltage, it's going to feed back a current. All right, so just get that. So if we have something that is dealing with series feedback, it means that we're feeding voltage from output back to input. And if we're dealing with something that is using shunt feedback, remember shunt is something that adds in parallel. Series, well, of course, is in series. The shunt circuit means that we are feeding back current. All right, just some little terminologies that you may have met already in other places. Now, what are the effects of feedback? Basically, we do this because there are certain things that we try to improve. If it didn't have a benefit, then there's no reason to try to put feedback around any sort of system. And in our case, and remember, you could probably just negative feedback, huh? For the case of amplifiers, not positive. Negative feedback, and I'll just talk in general by saying feedback. Feedback tends to increase the input impedance, and we'll just mention that when we look at the configurations of the amplifiers. Remember, it's always good to have a high input impedance. The higher the input impedance is the less current you're going to take from your source. So for instance, if you have a device or an amplifier that is measuring the voltages given off by, for instance, your muscles, when muscles are moving, you're talking about incredibly small voltages. So therefore, what you have is that the input impedance of any circuit has to be very high so that it doesn't, that all of that small voltage will appear across the input and not across any source. You also want a low output impedance so that when you're driving another a load, that most of the output of the circuit, and in this case amplifiers specifically, most of the output will drop across the load and not across the output impedance of the device itself. In other words, you wouldn't waste your energy on the power of the system. You want to stabilize the gain of the amplifier, that the feedback wants to stabilize the gain of the amplifier, because most devices are composed of individual components. Even an operational amplifier, we see the block diagram from the operational amplifier, but remember internally the piece of silicon has many transistors and resistors that are have been configured to make the circuit. So even at the silicon level, there are characteristics of the devices that vary. The packages get warm. All right. There are certain variations, well, specifically in temperature, but there are other variations as well. And what happens is that the characteristics drift, which is why when you watch things like a data sheet, you see them give you typical values, but they give you minimum and maximum, and sometimes values that drift according to temperature and so on. So what we find is that feedback tends to stabilize the gain of an amplifier against the sort of fluctuations of the characteristics of the device. But the trade-off is that it lowers the gain. So whereas if you have the open loop gain of the amplifier, which is the gain of the amplifier without any feedback, if it is at some value, when you supply feedback to the amplifier, the gain is going to drop. So you will have to factor that into your manipulations. But the gain that you get is that if the components and so on vary around the place, that the gain of the amplifier is not going to fluctuate too much. Then the frequency response, so you can increase the bandwidth of the response of the amplifier with feedback. And then some other things that we'll just mention on the fly, the linearity of it. You remember many devices, the input-output characteristic, we kind of assume that the input-output characteristic is a nice straight line, but sometimes the straight line is only for part of the operation. So it might do something like this and then straighten up for a part, and you sort of confine yourself to the linear operation. Feedback will flatten that for you and give you a wider range of linearity. Lowers the distortion, which we won't be talking about, but distortion is the changes in the signal as compared to the input, and reduce noise, which we're not going to talk about as well, but just in comment on the noise that we're talking about here is electronic noise, right? That is at the silicon level. I don't know if when you did physics or maybe when you started to do electronics, the things like shot noise and thermal noise, that thing that is proportional to absolute temperature and Boltzmann constant and so on, right? That's the kind of noise here that you're talking about. Yeah. So the configurations, we basically can classify amplifier systems into 4 types. The voltage amplifiers, which are the ones that we tend to meet all the time, right? You've been seeing that and working with those all the way through. Current amplifiers, transconductance amplifiers, and transresistance amplifiers. So we'll just walk through those and then just comment on the sort of equivalent circuits that are used. And I'm going to ask you to remember 2 things that you encountered early on. One was Thevenin's theorem, and the other one was Norton. Right, those 2 theorems you used in circuit analysis, and basically they do the same thing essentially, just depending on whether they want to deal with voltages or currents. One replaces a whole set of passive components and the behavior of the passive components with a voltage source and a resistor. The other one does the same thing, but it replaces it with a current source and in parallel with a resistor. One is a series. The Thevenin's is a source in series with a resistance. The Norton is a current source in parallel with a resistance. So the voltage amplifier, which is one of the common ones that we've dealt with all over the place, it accepts a voltage at the input and delivers another voltage at the output. And there's a gain to it, which is AV, which is the relationship between V out and V in. The model that we use, because we're dealing with voltages, is a Thevenin model, so that we model the input side of things as a source and a resistance, and we model the output as also a source and a resistance, right? And this particular output voltage source, right, that is where the gain, it's the gain on the input. So whatever input you put, you have the gain. That voltage source has a gain on it that passes through the output resistance to the load. And ideally, of course, we want the input resistance to be very high, as we're saying, because so that we want most of the input signal to appear across Ri. If Ri is much higher than Rs, then Vs and Vin are, for all intents and purposes, equal. In theory, Ri is supposed to be infinite. And similarly, we want the output impedance to be as low as possible, so all of the amplified voltage appears across the load. In theory, RO should be a short circuit, so AVVI is appearing across the load. Yeah? Make sense? So this is looking at it from a model point of view rather than from the transistors and so on. And there's things you would have met already, I'm sure. A current amplifier, and we'll get some, we'll touch on some circuit examples in a while, what these things might look like. And some you have met already. The current amplifier, of course, takes a current at the input and delivers a current at the output. So because we're dealing with currents in this case, we are going to use the Norton circuit, the Norton equivalent circuit, so that the input is the input section we model as a current source in parallel with a source resistance, and the output is a current source in parallel with the output resistance. And again, in this case, you want, for the current amplifier in this case, you want the input resistance to be low, because you want, when the current, you don't want any resistance to the input current coming into the device. And then on the output case, you want the output resistance will be high. So the parallel combination, because RO is in parallel with RL, RO, that the output, the overall impedance of the output will be closer to RL. And of course, there's a current gain. So the current amplifier has a gain AI. That is a relationship between the output current and the input current. Yeah. Next, the funny hybrid ones, the transconductance amplifier. And again, in a couple of slides, we'll see where what these may look like and where you're going to encounter them. The transconductance amplifier now takes a voltage at the input and gives me a current at the output. So we model, because the input now we're dealing with a voltage, we're modeling the input as a Thevenin equivalent. So that side is a hybrid now. So the input model is a Thevenin, which is a source and a resistance in series. And the output is a current because it's supplying current. So the output is a current source in parallel with a resistance. And in this case now, voltage in, so we want the input resistance as high as possible so that we drop as much of the input voltage across here. And then we want the output resistance as high as possible so that the parallel combination of RO and RL is close enough, is almost identical to RL, so that all of the current is going to flow through RL rather than RO. And of course, in this case, the gain of the circuit is a gain. You take the input voltage and there's a transconductance gain GM, which is IO over Vin. So the output, the change in output current over the change in input current, that gain called the transconductance GM. And then the last configuration here is the transresistance amplifier. So this does the opposite. This takes a current coming in and it's going to give me a voltage coming out. Because we're dealing with current, the input circuit, the input model, of course, here will be a Norton type of circuit, a current source in parallel with a resistance. This one is generating a voltage out so that the output is going to be a voltage source in series with a resistor, in other words, a Thevenin type. And in this case now, we want a low input impedance and a low output impedance. The low input impedance so that most of the input, when the voltage, when the current flows in, that most of the current is going to flow through the input resistance here of the circuitry, and then a low output resistance so that the voltage here is dropped across RL with as little loss as possible. And the amplification characteristic, of course, for this device is the transresistance, which is the ratio of output voltage to input current. So we can summarize all of that in one little table here, right? So each of them, this summarizes everything for the 4 types of amplifier, which are voltage, current, transconductance, and transresistance. Each of them, therefore, the transfer function, if you like, the ratio between its input and its output, or its output and its input, is given by these expressions here. Right, so all of them have a gain of some sort. The gain is either a voltage gain, a current gain, a transconductance, which is a change in current with respect to an input voltage, or a transresistance, which is a change in output voltage for input current. And these are the sort of characteristics of what we would want for each of them. The input impedances and the output, well, I'm saying impedances, but the input resistance and the output resistance. The more general term would really be input impedance and output impedance if you were to do this a little more advanced. So, right, so that's enough on a model side at least, but what does these things and where look like and where you encounter them? Well, of course, the voltage amplifier you've met all over the place already. Your typical, for instance, the one on the bottom left is a common emitter transistor. That's the one with the sort of H-bias type circuit, right? And on the right-hand side, you have the non-inverting operational amplifier. So those are voltage amplifiers that you're well aware of. they gain depending on in the case of the transistor, some characteristics of the transistor, and the load resistors coming out, and on the other end, the operational amplifier, they gain depending on the ratios of R2 and R1 in this case. So you've met that before. The current amplifier, actually, we met when we spoke about the regulated power supply. And in fact, the pass transistor in the regulated power supply is working as a current amplifier. It's amplifying the base current by the current amplification factor of the transistor right there. So this is a simple example that you would meet on a fairly regular basis when you use the transistor in such a way that it is amplifying its base current to provide a higher current output. Is working as a current amplifier. The transconductance amplifier now is something that is also known as a voltage controlled current source. Basically, it's a voltage to current converter, right? You take the voltage comes in, and then you generate a current in proportion to that voltage coming out. Now, one very common place that you're going to see it is in controls engineering, in like, for instance, process plants. Somebody had mentioned this before, and it came up in the lecture with Dr. Radix, for instance, that for instance, a typical process plant, how they send signals from one point of the plant to another is using something called a current loop. And they vary the current, the current goes between a low of 4 and a high of 20 milliamps. So currents flow through, you have sensors at some part of the plant, and the sensors invariably would create a voltage in proportion to some sort of behavior, right? So you have thermocouples, or you have flow sensors and the like, and they generate a voltage in proportion to whatever is happening at their end. But to send a voltage a long distance is a little bit of an issue because of line resistance. But if you were to convert the voltage to a current in the form of a current, source current, then you can force that current down a line, almost an infinitely long line with very little loss. And this is what they do. So they at one end now, you have the voltage generated by the thermocouple or whatever the device is. It goes through a transconductance amplifier or type of circuit that converts it into a current. And the current is now connected to a transmission wire, shielded wire, or wires. And they go from point A to point B, could be hundreds of meters down the road, to the next place that it has to be processed. Usually they make their transconductance amplifier is made with operational amplifiers. So more often than not, if you were to search for components, you're going to see something called an operational transconductance amplifier, which just means that it's made from using operational amplifiers. And the block diagram there is one made by a company called Renesas. And if you look at it, what it's doing essentially is that the voltage comes in, and notice the transconductance circuitry inside of here. If you go on you check on the data sheet for this, they explain very nicely how it works. But basically, the output voltage is GM times EN. EN is a differential voltage coming in to the device from whatever it is. GM you can control by there's a pin here that they have that allows you to control the value of GM, which is the transconductance for the device. And you can, by varying the current going into there, you can vary that value of GM and therefore get a current that is in proportion, well, basically within the limits that you needed to operate on. So if you needed to operate between 4 and 20 milliamps, you would adjust I ABC to give you a GM that will give me some output current in that zone. And they give you some typical values there and in the data sheet for the device. All right, so that's a transconductance amplifier. And of course, now when you reach the other end of the device, and I'll get to the circuit that I have there in a little while, but when you send the current down the road in the control plant, now you're going to have to convert it back from a current to a voltage to do some other processing. And this is where the reverse process comes in. At the other end, typically you can have something called a transresistance amplifier. In the literature, they sometimes call these things transimpedance. So you're going to see that term crop up every so often. And when you see that, they really mean a transresistance amplifier. Okay, so sometimes you see it as a transimpedance amplifier or a current to voltage converter. And then, of course, there's some very simple applications where you can create transresistance behaviors. For instance, there are certain devices whose output are inherently current. For instance, a photodiode. When the photodiode is on, it conducts current, a certain amount of it conducts a certain amount of current depending on the level of the light that is impacting on the photo diode itself. And that, if you were to wire it up in a simple circuit, then what you have there is an amplifier that is producing an output voltage, in proportion to that current that is being produced by the photodiode. So that's a very simple circuit that operates in the transresistance mode. And of course, the gain of the device is V out over R in, which V out over I in, which is that RM factor that I have here. And I have a little question down at the bottom. The simplest current to voltage converter is what? What is the simplest possible current to voltage converter that you could get? Yeah, a resistor. Right, so a resistor is a very simple, well, not very, it is the simplest current to voltage converter. You pass a current through the resistor, you get a voltage coming out of it. So in fact, you can make, there are many, the same voltage amplifiers that we have before. If I were to go back a couple of slides, right, depending on where you were to put, for instance, on this circuit here, if I wanted to sense a current and amplify the current, I can use, if I have a voltage coming in and I wanted to sense the current, I could use the voltage across, put the voltage across the resistor and you have the current in it, right? And similarly, if I wanted to feed back a current, I just have to pass the current through a resistor, it generates a voltage and I could feed it back into the circuit. So a resistor will appear almost in all of these sort of designs around at some point in there. Yeah, makes sense. So some configurations there. How do you look at that equation? No, there's multiply. There's pure. Well, I'm assuming that the asterisk is not convolution, right? Here multiply. RM multiply by I. Yeah. So RM I in, right? But just the fact that I could be either positive or negative, right? True, I'm a custom dealing with you in signal. So if I see RM on this, right, you had me wondering if you're talking about convolution, right? But it isn't. Right. So now, if we were to apply feedback to these four system, what's that? Output equals system, yeah, multiply. That asterisk I take in again, multiply, yeah. Right, user X. No, I know the multiply is really from programming. But anyway, so if we take any of the preceding four amplifiers, so we have the voltage amplifier, the current amplifier, the transconductance, and the transresistance, we can, if we apply feedback to it, we get four categories of feedback. The voltage amplifier, of course, if we feedback, we have to sense an output voltage and combine the output voltage with the input voltage, right? If it's, and of course it's negative feedback, so we call that voltage series feedback. The other voltage device that produces, the other amplifier that produces a voltage at the output is the transresistance amplifier. So voltage output, but the input is current. So we have to take the voltage at the output and we have to feedback current. Current has to go in parallel. Remember the model for it, the input model of it is a Norton circuit. So therefore we have to feedback the feedback current in parallel with that. So the transresistance amplifier is a voltage shunt system. The transconductance amplifier, of course, is the other way around. It's voltage on the input, current on the output. So what we're feeding back is voltage. So the voltage will be in series with the input. And then, of course, the current amplifier, you're feeding back current. So you have to feed current back in parallel with the input. So that's the current shunt feedback. So the two voltage devices are the voltage amplifier and the transresistance, and the two current amplifiers are the transconductance and the pure current amplifier. And those configurations, again, these are just, this is how it works. So when you get the actual circuit, and we at the end, the last sort of thing we look is just to see how these are actually implemented in an actual circuit. So the voltage series feedback, we start with a voltage amplifier here, right? Remember the voltage amplifiers are Thevenin input, Thevenin output. So we sense, if we're feeding back voltage, so we have to sense the voltage across the output, and we have to feed back the voltage here. Notice the polarity of the voltage. In other words, here's negative and here's positive, right? That's how we're getting the negative feedback coming in, so that the actual feedback voltage is being subtracted from the source, right? Remember, that is negative feedback. Of course, the open loop gain is V out over V in, and the feedback network is taking VF, sorry, is taking some V out and multiplying it by some gain factor beta, so that VF is beta times V out, right? And this is kind of like the G and H that we did when we were talking about block diagrams. So the transfer function for H beta is really VF over V out, right? So VF is beta V out. In the case of the transresistance, which is the other one that is feeding voltage back, the transresistance has voltage coming out. So we're feeding back voltage, but this network, our G and H, our feedback network now has to take the voltage and feedback current, right? So that the feedback current is whatever what do you call it, the transresistance of that network is, I over V, and it has to go in parallel with the source. But again, we're dealing with negative feedback. So notice that the source current is splitting between IF and IS. In other words, I is being, the current I going into the amplifier, IS has been reduced by the amount of the feedback. That's a negative feedback again. And of course, the transresistance, you have the forward gain, which is the ratio of out over in. Yeah. So those are the two voltage feedbacks: the voltage series, the voltage shunt, and then current series now, remember the transconductance, what the transconductance does. We have G and H again in the feedback loop. Right? A transconductance amplifier takes voltage in and gives me current out. So if it's current out, I have to feedback current, I have to sample current to feed it back, in other words. Right? Take some of the output current and feed it back. But then feedback network has to convert that to a voltage. And again, we subtract it from the source voltage. All right? So once you get in once you get in your mind, what it is am I feeding back? What is it am I sampling? The feedback has to sample something. Is the output voltage or current? If I have to sample voltage, then I have to sample the voltage across the load. If I have to sample output current, then I have to sample current in series with whatever is the load. Yeah? So this is current series feedback, and the feedback, of course, how am I doing the feedback? If I'm feeding back a voltage, I'm feeding it back in series. If I'm feeding back a current, I'm going to feed it back in parallel or in shunt. And then, of course, the last one is the current shunt feedback, which is the current amplifier. So I am sensing current. So therefore, I have to sense the output current coming here. The feedback network has to convert that into a current to feedback, because the source is also current. So it has to go back in parallel with that and also subtract. Right? So notice again the flow of the current inside of here. Make sense? The gist of it is to remember what is the type of amplifier. So if I have to put feedback on that, if I give you a transconductance amplifier, the input is voltage, the output is current. So I have to sense output current, but I have to send back voltage. If I'm sending back voltage, the voltage has to go back in series. So that will be a series feedback, voltage series. Yeah? And so you go on. And of course, we know how to simplify a block diagram by now, right? You've had quite a bit of experience from that. We know if I give you this with negative feedback, that the overall transfer function is A over 1 plus A beta, right? We are accustomed doing it, of course, with G and H. In this case, we're using A and beta in the nomenclature for this course. So the transfer function of the whole feedback network is A over 1 plus A by beta. And they call the quantity A times beta is normally called the loop gain, right? So even in our own encounter, when we had G over 1 plus GH you could call the loop gain, but we tend to be a little more general because we're using it for much more general applications than this. So in this case, they call A, the product A and beta, the loop gain. And what it represents basically is the gain of the signal that travels. The signal went through the amplifier and is fed back and goes back into the input. So that is the function of the beta network and the gain of the loop of that feedback network, right? And of course, we are accustomed doing this as well, so we can express this in decibels. If I take 20 log of the transfer function, right, you get the first step here, of course, which is no big deal. If AB, typically AB is much bigger than 1, so we could ignore the 1. In which case, the problem simplifies to 20 log AF equal to 20 log A minus 20 log A beta. So that you can get an idea of the loop gain in terms of the open loop gain of the system and the feedback gain, what the gain is with feedback. And therefore, if somebody gives you an amplifier and tell you that it has a loop gain of 15 dB, that tells you immediately about the amount of gain that the A beta network is going to provide. You can convert that back to a number and get immediately an idea of what the actual gain is of the circuit. Yeah? All of these things we have encountered in various forms already. And just to conclude the discussion, of course, all of this thing, there are some things that have to be true. First off, is that the signal transmitted through the amplifier, let me go back here, right? So if you have the amplifier here, first off, the signal going from input to output must only go through the amplifier, right? In other words, it can't do this, right? It can't go that way. So the first thing is that the signal from the input must only go through the amplifier on the way to the output. The second thing is that the feedback system must only pass through the beta block. So going back through here, the feedback must only pass through here. In other words, there should be no path that way for the feedback. All right? And the third thing is that the reverse, whatever that feedback network is doing, is supposed to be independent. Remember, the feedback network is connected. The feedback network is connected to the output of the amplifier. It's connected to the output of the amplifier and the input on that summing network. This has to operate independent of that. In other words, the output of the amplifier and the input of the summing network, the load of that, this feedback network must operate independent of the load. If it is being affected by the load that is being shown to it by the output of the amplifier or the network, then our analysis about how feedback works and so on is going to fail, because it means as you vary the gain of the network, or you vary the impedances of the amplifier and so on going forward, then once you change one, you're going to change beta indirectly, which means that all the feedback calculations are going to go haywire, and that's the last thing that you want. Yeah? So everybody following what we're doing so far? What we did was we have 4 types of amplifiers, and the amplifiers, all of the amplifiers are amplifying voltage and current. They're either giving us voltage, current, voltage, current, or current and voltage. We want to put feedback onto them and see what happens. So the feedback has to feedback for each of the voltage currents going forward. We can feedback a voltage or a current coming back. So depending on the configuration of it, there were 4 types of feedback, which was the voltage series feedback, the voltage shunt feedback, the current series feedback, and the current shunt feedback. Any series expression in the feedback means that we're feeling what? Voltage or current? Anytime you see series in the feedback expression, are you feeding back voltage or current? It has to be one or the other, right? When you're feeding voltage back, remember what you're saying is that the voltage is coming in series, because you're feeding back the voltage now. It has to be in series with an input voltage. All right? So once you're talking about series feedback, it means you're feeding back voltage. When you're talking about shunt feedback, it means that you're feeding back current. So the first term here, right, telling you what you're feeding back. The second term going to tell you how you're feeding it back. Right? So for instance, first one here. So voltage feedback, we're feeding back voltage. series, it means that, sorry, we're sensing voltage and we're feeding back voltage. The other one, voltage shunt, we are sensing voltage, we're feeding back current. This one, we are sensing current and we're feeding back voltage because it's in series. And the last one, we are sensing current and we're feeding back current. Yeah? So those are the 4 configurations. Tomorrow, we're going to look now. We made some statements here. Where are we? Yeah, we made some statements here that feedback changes these particular parameters. So we're going to start in tomorrow's class and look and see how, by doing the feedback, how we increase the input impedance, lower the output impedance, how we stabilize the gain, and how we improve the frequency response of the amplifier, right? And at the same time, we'll put in some little circuits to show, well, you know, where, at what point of a circuit do you take the feedback signal? If you want a feedback of current, where does that appear in like a normal, a common emitter transistor amplifier, for argument's sake? Where, if I were a feedback, where is that feedback coming from, and how is it being added back? All right. So we'll start looking at all of that in tomorrow's class. Right. So we all right? Any major questions at this point? Of course, some of these things you have to digest it a little bit and look at them, look at the diagrams, and see what we're talking about. Okay, so if that's all right, yeah, you have to review, definitely.